Okay, so I'm going to talk about one other method that's a little bit superior to Bonferroni in some ways, but it's a little more complicated, so it's not quite as popular, I think. But let me quickly go through how this approach works. So this is known as Holm's method, and it starts the same way as Bonferroni. You just perform standard hypotheses tests on your M hypotheses and calculate standard p-values, p1 through pm, so it's exactly the same as before. But now what we do is we order the p-values from the smallest to the largest. So this p1 with parentheses, this represents the smallest p-value, p2 is the second, etc. So they're ordered from smallest to largest. And then we apply this rather strange-looking calculation where we try to find the first p-value where the value of that p-value is greater than alpha, say 5% if that was our cutoff, let's say, over m plus 1 minus j. So just to give you a feeling for that, suppose that j is 1, then the smallest p-value, we'd be looking at that and comparing it to alpha over m, or alpha over m plus 1 minus 1, so alpha over m, which of course is the same as the Bonferroni cutoff. So for the smallest p-value, we're looking to see whether that value is past alpha over m. If it's not, then we go on to the second p-value, and we ask, is the second smallest p-value greater than alpha over m minus 1? If not, then we go to the third one. Is that smaller than alpha over m minus 2, etc.? And we find the first point where we break that rule, where the p-value is above that value. And then we simply reject all null hypotheses where the p-value for that null hypothesis is less than this cutoff p-value. So this is also guaranteed to control the family-wise error rate, and it turns out that it often will reject more hypotheses than the Bonferroni method.
It's always going to reject at least as many as the Bonferroni method, right, Gareth?
Yes. So, and you can see that because you compare the smallest p-value to alpha over m. So if Holmes fails to reject that p-value, then Bonferroni won't reject that either. So again, let's look at this on the fund manager data. So I've ordered the p-values now from smallest to largest. And it turns out that when we apply Holmes' procedure, that the first two null hypotheses get rejected. And that's because the smallest p-value is less than 0.01. That's the alpha over m. But the second p-value is also less than alpha over m minus 1. And that turns out to be 0.0125. So now Fund Manager 3 just sneaks in under the threshold.
Right under the wire.
Under the wire, and is also rejected, which is a good outcome for the manager.
And just to be clear, that's Fund Manager 3 because P parentheses 2 is the second smallest p-value, and that corresponds to Manager 3.
Right. But of course, the other managers, the p-values are still very large, so we don't reject those. So this is just a very simple example of a situation where Holm manages to reject two null hypotheses, but Bonferroni does one. But both methods are controlling the family-wise error rate at 5%. And by the way, this is because Bonferroni is sometimes overly conservative. We guarantee the family-wise error rate's no more than 5%, but in practice it might be quite a bit less than 5%, so we've been overly conservative. These pictures here just illustrate one more way that you can see Holm beating out Bonferroni. So here we have 10 different hypothesis tests that we performed, and these are the p-values associated with those hypothesis tests, ordered from smallest to largest. The black horizontal line here is the alpha over m threshold that Bonferroni uses. So every point under that is rejected by Bonferroni.
So here alpha is 0.05 and m is 10, so that's the 0.005 level in black.
Exactly. And the blue line here is the cutoff for Holm after you order the p-values from smallest to largest. And you can see that it starts at exactly the same point as Bonferroni, but then is strictly above that. The black points are where both Holm and Bonferroni get the same conclusion, either rejecting or failing to reject. But this one red point you see at number 8 here is rejected by Holm because it's below the blue line, but is not rejected by Bonferroni.
So that's like the red one is a discovery that we made using the Holm correction, but not using the Bonferroni correction. And we want to make as many discoveries as possible, subject to controlling the family-wise error rate, so that red one represents a real win for Holm.
Exactly. And just one more picture to illustrate a more extreme example. Here, this is sort of unusually extreme, but this illustrates that here we've got only 3 hypotheses rejected by the Bonferroni approach, but we actually managed to reject 8 hypotheses using Holm. So potentially you can get a lot more discoveries this way. Okay, so which is preferable? Again, it just comes down to which you prefer. Bonferroni is a little simpler. Holm is slightly more complicated, though not dramatically. Both will reject the family-wise error rate. Holm is a better choice in terms of getting more rejections.
Well, I think this has to do with whether you're is it satisficer versus maximizer? Because I personally think Bonferroni is usually good enough, and Holm is just a little bit show-offy. But
yeah, and let's be clear.
I'm like just lazy to the level where I do Bonferroni.
And along with 99% of other people, because Bonferroni is by far the most popular approach here.
Yeah, but with alpha equals 0.01, Gareth can reject the null hypothesis because he's in that 1%.